In this short video, we will focus on why finite element method or FEM is required and how does FEM approaches to solve a problem. To understand the concepts, let's take an example of a simple rectangular bar. Let's assume that the bar is made of homogeneous material and has a constant area along its length L. The tensile load P is acting axially outward on the free end and the Qx is the tangential body force per unit length acting along the surface. In this problem, the variable of interest is the amount of displacement along the length due to the forces acting on the bar. The solution can be obtained by using differential calculus and is generally known as the exact or closed form solution. To derive the governing equation, an element dx is taken at a distance x from the fixed end. In static condition, the forces acting on both the faces of the element are equal. In the simplified equation, we substitute stress, which is the product of the Young's modulus and rate of change of displacement, to obtain the governing equation. Integrating the differential equation and applying the natural boundary condition, we get the constant C1, and C2 is obtained by the application of the essential boundary condition. Putting the values of C1 and C2, we get the closed form solution for displacement. In this simple rectangular bar problem, with the given length, area, Young's modulus and applied forces, we have to find the displacement for different given values of x. Using the derived analytical solution and substituting the given values, we get the value of displacement at distinct points along the bar. Now, consider a case when two different materials are diffused and the pattern of diffusion is unknown. Here, the Young's modulus is not constant. In the second case, the area of cross-section along the length is not known. In both these cases, the closed form solution cannot be obtained using calculus. There are several other cases where it is difficult, rather impossible, to find the exact solution. These are the cases where finite element method is required. These finite size elements have standard shapes and constant properties. Any arbitrary shape is approximated by a mesh of known elements interconnected at nodal points. In the same manner, the discretization of unknown material diffusion problem can be done, such that the constituent elements are well connected at the diffusion boundary. For each element, the equation F is equals to Kx is solved numerically by the computer program. If three elements are stacked, the force applied at one end will result in deformation in all the elements. For simplicity, the element is assumed to be one-dimensional, having two nodes, with each node at its end. The displacement of both nodes of an element can be written in the matrix form. The equation for the three elements are solved simultaneously. This is known as global set of equations. Let's go back to the rectangular bar problem and try to solve it using FEM technique. The various FEM methods transform the elemental governing equation into an equation of the form F is equals to Kx. We redefine the equation according to the variables of our problem. We have taken y to be the nodal displacement and x to be the position along the length. So the force equilibrium equation is F is equals to Ky. In FEM, we assume an initial trial solution which is a complete polynomial of order n-1. The n is the number of nodes on a single edge of an element. As shown in our problem, we have 4 linear elements, each having 2 nodes. So, the linear solution for the kth element is This solution is assumed with the condition that the value of the kth node should be maximum at its own position and should linearly decrease toward the adjacent nodes. The nodal solution should be interpolated in such a way so that the residue is minimized. Among the several weighted residue approaches, the Rayleigh-Ritz method is a popular approach. The Rayleigh-Ritz method minimizes the residue by equating the integral of the weighted residue form over the entire domain to 0. Here, the weights are the coefficients of the nodal displacement in the assumed trial function. Integrating the first term by parts, the second order derivative is reduced to the first order derivative. This is known as the weak form of the Rayleigh-Ritz method. So, the assumed linear solution will fit the first order differential equation. Putting back the derivative of the weights and the assumed solution in the weak form equation for each node, we get a set of equations. The first term is the stiffness matrix, which includes geometric and material properties of the elements, and yk and yk plus 1 are nodal displacements. The right hand side term represents the applied nodal forces. We will use these equations to solve our defined problem. Since in our problem we have taken 4 linear, well-connected elements and 5 nodes, we will have 5 nodal equations which are combined in such a way that the connectivity is maintained. We will get a global set of equations. Using computer program to numerically solve this set of equations, we get the nodal solution. These nodal solutions are interpolated over the length of the element. In comparison, the exact solution and the FEM based solution for our problem are observed to be equal at nodal points. If we plot the exact solution and the approximate solution, we observe that more the number of elements, lesser will be the error and better will be the approximation. But better approximation comes with a price, a greater computational time.